Hey, let's get started. So today's topic is model distillation, and with that, we will also talk about model extraction, which is kind of one way to use concepts from model distillation to attack models that are being hosted by companies, say, as an API. So before we talk about this, some logistics stuff. So we are working on the exam grading. It's partially graded right now and are aiming to be done by Sunday evening. So once we publish the grades, there will be a 1-week period from the point that we publish the grades that you can submit regrade requests. Highly encourage you to only submit regrade requests if you think there was an actual error in your grades. If you feel like you want more points or whatever, it's probably not going to go well, and scores can go down also if you submit a request. So make sure you're only submitting legitimate regrade requests. I have to say this because otherwise people just submit regrade requests for every problem, and it's not manageable. Okay, so your next 2 things that are due are homework 2, it's due May 4th, and then the final project report is due May 12th. So there are some questions about what you have to submit. So you have to submit a PDF version of your report. There will be a template for that on Overleaf that'll be released. It's a minimum of 8 pages of content, so that is excluding things like references and also excluding massive filler figures. So we're looking for a solid 8 pages at least of content. You also have to submit your code and a README alongside your code. The best way to do this is email us a public link to your GitHub repository for your project. Most groups last semester chose this option. You can also zip up your code and attach it in an email to us. But in either case, we expect every group to send the instructor's account an email with either a link to your GitHub repo or a zip file containing your code and README. All right, so, and you will have one more quiz, not this week, but next week, and that'll be the last of your quizzes. Any questions about logistics or projects or whatever? All right, also note that my office hours this week will be right after class, so 4 to 5 p.m. in case anyone has any specific questions. Okay, so the topic for today is knowledge distillation. So we've been talking about all these really big language models and how they're inaccessible to most people, right? Like you as a student with access to Google Colab cannot train something on the order of GPT-3. You can't even train a GPT-2, probably can't do a GPT-1. So you are limited to accessing these models through any sort of APIs that the company has made available, such as the one OpenAI has, or perhaps you're limited to using pre-trained models and perhaps fine-tuning them on your own small data as you're doing in the project, as you're doing in the homework too. But it would be much more accessible if we could have smaller models than these insanely huge 100 billion plus parameter models that are just as effective as the huge model, but have a much smaller footprint. So you can maybe even train or use them on resource-constrained settings like in your Google Colab. So some terminology, we call the small model in these distillation setups the student, and a large model the teacher. So the setting is that some huge company has trained a massive language model, and we want to take that language model and use it to teach a much smaller model to behave like the teacher. So this could be confusing at first, but let's check out how it's actually done. Also, I just wanted to show this figure as a bit of like historical record. So we're going to talk briefly about this model called Distill-BERT, which is a smaller version of BERT that was trained using BERT as the teacher model. This work came out in 2019, and they had this figure showing all of the models that had been released up till that point. So you have like Elmo with 94 million parameters, GPT-1, BERT large, this is the one they focus on, with 340 million parameters, GPT-2 with 1.5 billion parameters, then the biggest one they had was 8.3 billion, and now with the latest Google model, it's like 500 billion parameters. So you can see that this curve has been continuing. We've been following this curve, and who knows what's next. But what they're interested in is are the ones over here where the number of parameters is small, but as we'll see later, the performance is still pretty good. And one of the issues is that if I wanted to train a 66 million parameter model from scratch using like BERT's objective function, I'm not going to be able to match the performance of this much larger BERT model. So the trick in distillation is to use an existing large model to help make the smaller model make better predictions. Okay, so we saw this slide before when we were talking about knowledge encoded in these kinds of BERT-like models. So Bob went to the mask to get a buzz cut. If we pass this through BERT and see what the predictions are for the mask token, we would see that a word like barbershop might get most of the probability, barber, salon, stylist, all places you go to get your haircut. So remember when we are training this BERT model, right? We are giving it the ground truth word that appears in this mask token, and we're computing the cross entropy loss with respect to that single word, right? So our ground truth probability distribution has, let's say the ground truth sentence is Bob went to the barbershop to get a buzz cut. So here, when we're doing training of our BERT model, we have a distribution, our ground truth distribution, which puts 100% of the probability mass on barbershop and 0 for every single other word type in our vocabulary, right? That's how we discussed training these models. And one thing that we know if we look at the predicted distribution from these models is that there's a lot of useful information beyond just the actual word that occurs, right? So barbershop, sure, this is the ground truth word, but then barber, salon, stylist, these words have some probability given this context, and they're all useful in a way for understanding the context, right? These are all words that could be alternatives, essentially, in this context. So if we have a larger model that we've trained like BERT, that's giving us some reasonable, semantically meaningful probability distributions where even the top 3 or top 5 or top 10 tokens are telling us something about the context, then that's a lot more information than just a single token, which is what we get in normal training. So in distillation, instead of putting 100% of the probability mass on the word that appears in the mask, instead we have what's called a soft target distribution, where every single word type in our vocabulary gets some probability, and this probability is what is predicted by our teacher model, like a BERT large model. So let's say we have this tiny model, which is so BERT, let's say our teacher is a 12-layer transformer, and we're trying to distill it into a 6-layer transformer. So we want to train this student model, which is half the size of our teacher model. And so what we can do is we can take this same context, BERT went to the mask to get a buzz cut, we pass it through our Distill-BERT, or our small BERT model, and we compute, all the computations are exactly the same, except we only have 6 layers. So when we get to the 6th layer and we pass this representation for the mask token into our softmax, we're now going to get a distribution over all the word types in our vocabulary, and we are going to compute the cross-entropy loss using the predicted distribution against the soft distribution that is output by the teacher model. So now, the probability of my student model of predicting every word type, we're matching every word type's probability against the corresponding probability output by the teacher model. So we're getting a lot more information. For this particular context, the student model has to assign 54% probability to barbershop, 20% to barber, 6% to salon, 4% to stylist. So we're not just putting 100% of the mass on barbershop. Okay, so remember when we talked about the cross-entropy loss, we talked about it in the context of this like maximum likelihood training where we're putting 100% of the mass on the ground truth token. And so when we discussed this equation, it turned out that we didn't actually need to sum over all of the word types in the vocabulary because the target probability was 0 for all but one of the tokens. So this just reduced to the negative log probability of the target token. But that doesn't happen in distillation. So in distillation, you actually have to sum over every single word type in the vocabulary because the target probability is non-zero for all of those tokens. Yeah?
The main motive of distillation would be to check if we can represent the same amount of knowledge with a smaller architecture.
Yeah, so the motivation is the teacher model has encoded some additional knowledge about each context in its output distribution, right? In this example, the top 4 words are all places you might go to get a haircut, right? So the idea is that you want your student model to match the distribution that a teacher model is producing. Okay, any other questions?
So the training for the distinct word would be still longer than the normal word, right? Because for every sentence we need to actually pass it to the teacher word to get the output soft targets, and then we'll be using it as a target for the distinct.
Yeah, that's a great point. So in this kind of setup, for every single training example, I need to do 2 things. First, I need to run it through the teacher model, get the distribution for the mask token. Then I need to run it through my student model and compute the cross-entropy loss with respect to the teacher distribution. However, you can make this a little faster. So depending on what kind of hardware you have, you can cache all of the teacher model's predictions for some largish training set. Because remember, the teacher model is not changing here. It's a fixed model that has been pre-trained. So there are some hybrid strategies as well. Like you could potentially compute the teacher targets for a very, very large percentage, maybe like 5% of your training data. Then you can train your student model on those predictions and have a separate process that's computing the teacher's predictions for the next 5%. So there's many different ways you can do this to avoid, but yeah, it is going to have this extra step that's not there in training from scratch. Okay, do we take the loss over the top K soft targets or over the entire soft target? In distillations, usually the entire soft targets, not the top K soft targets. So your loss is, the summation is over the entire vocabulary. And you can even see how this might be useful even for tokens that are not in the top, like even 10,000 most probable tokens. At that point, or maybe like 1,000. At that point, you might get some knowledge about like parts of speech that are appropriate in this context. So maybe the top 1,000 most probable tokens are all nouns, but then once you get past some point, you start getting other parts of speech which don't make sense in this context. Even just having that relative ordering of parts of speech is useful for the model to learn something about this context. So it's giving you a lot of additional information over the normal training. Yeah. The question is, would Distilbert also have the next sentence prediction task that NormalBert has? I'm not actually sure what they did in Distilbert, but you could certainly distill that classifier as well. So you could just use the predicted distribution from from the teacher BERT's next sentence prediction classifier over the CLS token and just do the exact same thing here. I don't know if they actually did that or not, but it's certainly possible. As we'll discuss, you can distill many other things, not just the final predictions for the token predictor. Okay, so just reiterating what I said again, instead of a one-hot ground truth distribution, now we have a full predicted distribution. As we discussed, more information is encoded in this full teacher distribution than just the correct word. And what I was saying before, the relative order of low probability words, like in this example, church is probably not semantically plausible in this scenario, but it's syntactically valid. But and, Bob went to the and to get a buzz cut, doesn't make sense. So even the ordering of these two words gives you some information about the context. Is it necessary that both teacher and student have the same vocabulary? Yeah, in this case it is. So the output label space needs to be the same, so you need to have a probability for every single label in the teacher model needs to have the corresponding probability in the student. Okay, so the Distill BERT results back from 2019 show that it retains 97% of BERT's performance while being only 6 layers. So BERT had 2 versions, BERT base, which was 12 layers, BERT large, which was 24 layers. So you are shrinking the model by quite a bit. If you look at the performance on the glue benchmark, BERT base gets a 79.5 average score over all 9 of these different classification tasks. Distill BERT is getting 77. So on some tasks, it's quite a bit worse, but overall, it's doing pretty decent and still much better than Elmo. So it's retaining a lot of the performance advantage of BERT while being smaller. Okay, so back to your question. There are many other components in BERT that you could imagine distilling. So why should we just stop at the final probability distribution for the mask token? There are several other things that could be distilled. So for example, we could distill hidden states. We could distill attention patterns. So let's say my student model has 6 layers and 8 heads in each layer, and my teacher model has 24 layers and, I don't know, 8 heads in each layer. Here, you can say maybe you want the first layer of your student model to attend over the same things that the first layer of the teacher model does. So, as a question to you all, how would you, if you wanted to apply distillation to the attention distribution, the self-attention distribution of a BERT-like model, how might you do that?
Like when you do attention, you take a softmax over the shot register model tokens. Like, could you do just cross-country loss between their softmax distributions? Yeah,
So you could certainly do that, right? Because you're getting a distribution over the different positions in your input. So you have 2 probability distributions. You can compute the cross-entropy loss and add that as a loss to your normal, like, mask language modeling loss. So what if you wanted to do distillation on the hidden states of the model? So this is a little bit different. So here, let's say you want the first layer's token level representations from your small BERT to be as close to the first layer representations of the teacher BERT as possible. What might you do here? Yeah. So here you have 2 dense vectors, right? They're no longer distributions. So you have the teacher's hidden state and the student's hidden state. You can compute the L2 loss or the square loss or whatever we called it, and add that as a term to your loss function to do this distillation. So in Tiny BERT, which was proposed the next year, they added these kinds of additional loss functions, so attention-based distillation and hidden state-based distillation, and got some additional gains this way. Yeah.
Does the distiller have the same size and states as normal bird?
So I'm not actually sure about the hyperparameters, but in Distilbert, there's no need for that to be the case, because you're only distilling the final probability distribution. In this case, though, you probably do, because you're doing distillation on the hidden states themselves. So if they're of different sizes, it's going to be difficult to compute this loss. Yeah. Any other questions? Okay, so this is one way that you can take a really big model and make it smaller, and you will lose performance, but it's much better than training the same small model from scratch, as we'll see here. So in this paper, well-read students learn better. They did an empirical exploration of several different strategies for training a small model. So these plots are a little bit confusing, but I'll try to explain. So on the x-axis, we have several different model sizes, and these are all like BERT-like models. So they have 2-layer models all the way up to 12-layer models, and they're also varying the dimensionality of the hidden state. So to the left are the smallest models, to the right are the biggest models. Now, there are also 5 different configurations of models that are on these plots. So the dashed red line at the top, I think it's visible, is the teacher model. So I think in this paper it was a BERT large, like a 24-layer BERT model. And you can just see its performance. It's basically like kind of an upper bound. So we're trying to get a smaller model that reaches this dashed red line, basically. So then let's start from the bottom here. Basic training means, so we're looking at 4 different data sets. This is entailment. This one is also entailment. This is sentiment analysis, and this is sentiment analysis as well, just 2 different data sets. So let's take a look at the entailment task. Remember, this is the task of given 2 sentences, do they contradict each other or entail each other, or are they neutral? So in basic training, I'm going to take this model, whichever size it corresponds to, randomly initialize all of its parameters, and then train those parameters from scratch on this entailment data set. So this is like the worst thing you could do. There's no pre-training involved. You're just training on the labeled data set. And you can see that in all of these data sets, this is the one that does the worst, which we would expect, because there's no self-supervised training that's making this model learn some general properties about the language. So next, we have normal distillation. So this is when we take the teacher model, we randomly initialize the student model, which is of any of these sizes, and then we train that student model from scratch via the distillation objective. So this, instead of just using the ground truth training label as the form of supervision. So here you can see that this always does better than basic training, but it's not really close to the teacher model. So there's still a big gap. You're losing a lot of performance when you're distilling into the smaller model. So then there's pre-training and fine-tuning. So this blue line, it has no distillation at all. Basically, you take this model, the student model, you randomly initialize it, and then you pre-train it using the masked language modeling objective on some large data set. And then you take the pre-trained model and you fine-tune it on the labeled data set. So here, there's no interaction with the teacher model, but you can see that it's still pretty good on all of these data sets. And this shows you basically the power of pre-training and fine-tuning, which we've been talking about this whole semester, right? This is the transfer learning gap. So you can directly compare this blue line to the basic training line, this dashed gray line with the X's, And the gap there is basically what you get by having pre-training before you train on your labeled data set. And you note that on most of these data sets, except for this Amazon book reviews one, pre-training and fine-tuning the smaller model is better than just normal distillation. So you might think, well, why would I use distillation? I can just pre-train my smaller model and then fine-tune it, and it does pretty well. But they find that a fourth strategy actually works the best. So here, you start with your student model, you randomly initialize it, and then you pre-train it on masked language modeling. And then you do distillation using the teacher's labels. And then finally, you do some additional fine-tuning on the ground truth data. So you basically mix in both the distillation objective as well as fine-tuning as you would normally. And this seems to be slightly better than all of the other approaches on most of the data sets, and sometimes it even reaches or exceeds the performance of the teacher model. So just to explain some of these different techniques that are going on in this last configuration, we have our compact model, so that's the one that's plotted in all of these plots. The very first step that is crucial is doing pre-training. So we take some unlabeled data and we do masked language modeling just as we've discussed with BERT, except we're pre-training a much smaller model. So in this case here, we're pre-training a 2-layer transformer with very small hidden states. This is something you could feasibly do on Colab. So once you're done with pre-training, then you do distillation, where you're taking the predictions of the teacher model on the MNLI data set and also potentially on the unlabeled data set for masked language modeling. So you can do distillation on both the target task predictions as well as the pre-training tasks predictions from the teacher model. And then finally, you can do an additional step of fine-tuning on just the target data set with like 100% of the probability mass on the correct labels. So all of these different techniques in combination seems to work the best for getting a compact model. And you can see that using all these techniques, there's a huge gap between that and the basic training with no sort of pre-training or distillation. It can be, like 15 points here, and yeah, I mean, it's a huge gap. So training smaller models is hard, and you might need all of these kinds of techniques if you're going to try and get the best performing smaller model. All right, any questions?
What's up with the Amazon book reviews where it's better than the teacher? Like, how?
Yeah, I think some of these are kind of random effects. Like, it's hard to know how significant of a difference this actually is. Probably what we might want is for them to have run several different versions of the model with different random seeds and done a proper analysis, but it's also very expensive to do so. I'm not sure what's going on with this data set. So yeah, I would suspect it's some sort of weird random effect. I would not draw the conclusion that this approach is always going to be better than a large teacher. That seems, although there are, some approaches where the goal of the distillation is to get a better model than the teacher, but in those cases, the student can actually be bigger than the teacher. So there's many different configurations of this setup. In this case, I think it's hard to expect the smaller student to do better. Yeah, so the question is the pre-training of the compact model done on the same scale as the pre-training on the large teacher model, the same data set and so on? Yeah, so that's quite expensive, right? But that also improves your performance significantly.
So actually, it's like different people with large teacher versus learn from another large teacher. I mean, so what's the difference between the pre-trained model and the large teacher? I mean, besides
Yeah, so the difference is that the small model that you're pre-training could be like much, much smaller than your teacher, right? In this case, it's only 2 layers model compared to 24 layers. So
But it's pruned exactly as a large teacher is pruned.
it's pre-trained just like the large teacher, but the pre-training will take much less time because the model is smaller.
Do you think it would be advantageous to pool the parameters of a large model into a small model?
So the question is, could we pool the parameters of a large model into a small model? Perhaps we could. So let's say we have a 2-layer student and a 24-layer teacher. Perhaps we could just select 2 layers from the large teacher, initialize our student with those 2 layers, and then fine-tune it on our target task. Maybe this will do better. You could, but it's not clear that those layers are the best ones to select and the most reasonable in combination. So next we'll look at an approach that is not as crude as that, but still manages to reduce the size of the model by selecting certain parameters from the teacher. Yeah, actually it's a good segue into this next part. So let's say you want to get a smaller model out of a larger model, but you don't want to go through all of the stuff that we've talked about, like with distillation and pre-training a small student and so on. Can you just take a huge model and find some subset of the parameters in that huge model that are contributing most to its performance and prune, or so basically remove all of the other parameters in the model? And still retain the same performance. So there is this work in 2019 called the lottery ticket hypothesis, which is a hypothesis that says that given some, pre-trained network, some neural network that has been trained on some task, there is a subnetwork of that task. Of the large network that, if you randomly initialize it and then train it in isolation, you will get the accuracy of the original network back after training for the same number of iterations. So this is kind of strange. Here, you're reducing parameters mainly through sparsity. So you take some percentage of the original model's parameters and you mask them out, so you set them to 0, and only a small subset of the network is allowed to actually learn non-zero parameters. So if you look at this, you first randomly initialize some fully dense neural network, and you train it on some task, let's say sentiment analysis, for j iterations. So after you train it for j iterations, you get these parameters theta sub j for your neural network for the task. And now in step 3, we are going to prune a fixed percentage of the parameters in theta sub j, p% of the parameters, by creating some sort of mask matrix where it's a 1 where we're going to keep that parameter and a 0 when we're going to prune it. So how do we select this pruning process? In this first paper, they use a very simple process for removing weights at each layer. They just remove the weights that have the lowest magnitude in each layer. Since this was developed, there have been many other approaches that are more intelligent. There's methods that kind of prune whole columns of the weights, so you can actually reduce the dimensionality without having to rely on sparsity to get the advantages of this approach. So anyway, so you prune this network and you make this mask, this binary mask, and then all of the parameters that remain, so where the mask is 1, you're going to reset them to their values in the random initialization. So this is theta sub 0, not theta sub j. And the theory is that if you train this network where most of the parameters are 0, p% of the parameters are 0, and only these other ones that had the high magnitude in this initial first 2 steps are remaining, you can train a network that kind of matches the performance of having all of these parameters. So the intuition here is that there's, in any given network, only a smaller subset of the parameters that actually contribute to solving the task. Many of the parameters might be redundant or unnecessary or maybe never used at all during the training process. There could be like dead neurons that never get activated. There's many different things that could be going on. In this paper, the lottery ticket for BERT networks, they look at this kind of pruning strategy applied to BERT models on a variety of different tasks. So here you can see that they have the full BERT base performance. So this is this middle column. This is kind of the baseline, what you would expect to get when you run BERT over, like you pre-train BERT and then fine-tune it on each of these different tasks. And then you see that they are able to set some very high thresholds for this pruning process. So for MNLI, this entailment data set, they have a sparsity rate of 70%, meaning 70% of neurons in BERT base can be zeroed out, and the resulting neurons can be trained from scratch and still achieve, in this case, in even like slightly higher performance than the original network, despite only 30% of the parameters being non-zero. And you can see here that in all cases, you can have like pretty high sparsity values while still retaining the performance of the original network. So now this kind of pruning does not automatically come with speed ups because you're not actually making a smaller model. You now just have a model that has a lot of parameters that are zero. You have to use kind of libraries or implementations of these models that have some sort of sparse computation built in that can take advantage of this kind of setup to see those speed ups. So it's not, even though it's much easier to do this than it is to go through the pre-training and distillation kind of stuff, the actual speed ups that you get from this are probably not that large. In fact, the original papers don't even report any sort of timing experiments because it's not really clear what kind of libraries you're going to use to get those speed ups. But since then, there have been works proposed that have some sort of useful sparsity where, for example, if you zero out an entire column of a weight matrix, you can basically just drop it, and then the resulting hidden state is also compressed. So you can have a completely dense network after pruning, which actually gives you these speed ups. Okay, any questions about distillation or, yeah?
In the lottery ticket, the previous slide, we were initializing the weight back to theta 0, the ones that are
Yeah.
Why not utilize the ones that were like using theta J as a starting point?
So the question is, why are we initializing these theta 0 and not to theta j? I mean, this is just kind of empirically demonstrating this hypothesis. So it's not really to get a better model or anything like that. It's actually quite fascinating that this works because it's essentially saying that for every random initialization of a dense network, only p% of the neurons after going through the whole training process actually seems to matter for the full performance of the network. So it's more of like helping to understand the structure of these networks rather than trying to get a performance or speed improvement. But yeah, this kind of work has also inspired many practically useful pruning techniques. In transformers, for example, people have found that you could prune attention heads. So this is an actual, like, it'll give you real measurable speed ups at test time if you replace 16 heads with one head. But it turns out that a lot of those heads are redundant, or some of them don't actually mean much or contribute anything at all to the prediction of the next word or the masked word. So yeah, this kind of pruning as a methodology can be used to both understand better what the networks are doing as well as optimize them.
then fine tuning on these downstream tasks to see how the sparse network is doing.
Yeah. So in this paper, they do the exploration both at the pre-training and fine-tuning kit. I think here this is the MLM result, so for pre-training itself. Yeah, and I think these results, they start with the pre-trained BERT model, and then they are exploring the fine-tuning process. So if you fine-tune BERT for this many iterations or something. Yeah. So it's a different subset of neurons that are pruned for each data set. As you see here, the sparsity is changing for each. Yeah, so you're definitely wasting some computation, but again, the goal is not to get any speed ups or anything like that. It's just to show that this is possible. Okay, so the final thing that we'll talk about now is switching from understanding these models and making them faster and smaller to more of intersection between NLP and security. So you can use some of the techniques that we talked about to steal models. This process is called model extraction, and it is a huge concern for anyone who is actually deploying their models to users through something like an API. So let's think from the perspective of, let's say you have something like Google Translate, and you don't want to keep paying Google to use their Translate service, so maybe you want to leverage Google Translate to train your own version of Google Translate that performs exactly the same, but that you can use for free and not have to pay Google anymore. In this kind of setup, you don't have access to a number of critical pieces of information or modeling. Like, you don't have the model that Google Translate is using. You don't even know what model they're using. You don't have their training data. You don't have the distribution over words that is predicted, right? You just have, in the case of Translate, you just have one output from, say, a beam search from their model. So you have very limited information. In this kind of setting, if you're an attacker, can you still get some useful information to extract this model? That's the question that we're looking at here. So my own student, Kalpesh, worked on this a couple of years ago in collaboration with Google, and many people have worked on this kind of model extraction in other settings as well, so computer vision and many other things. So we are referring to these model extraction or model stealing attacks as those where let's consider this example where there's a company that trains a binary sentiment classifier, say based on BERT or based on any sort of pre-trained model. We'll refer to this as the victim model. So this is the model that we're trying to steal as an attacker. So this works as follows. A user will provide input to the victim model. The victim model is a black box from the perspective of the user. So you don't know what kind of model is being used, and you don't know what the parameters of the models are, and you don't even know what percentage, what probability the model assigns to positive and what probability assigns to negative. You just get the argmax prediction. So it's a total black box setup from your perspective. But there is some API where you put in an input and you receive an output from this model. So it's a black box. We can't see it. So obviously, if we knew what the model was and we knew its parameters, we could just copy the parameters and we would. So of course, they're not going to make the parameters available to you. Okay, so let's now say we want to attack this model. And this is the setting that we found actually works to steal a number of Google NLP APIs for quite cheap. Let's say you're an attacker and you want to steal the sentiment model. So I can put in sequences of completely random text. This costs me nothing to create, right? I can just sample words from a vocabulary. I don't have to find real sentences. I don't have to find sentences that contain any sort of sentiment even. So that could be kind of expensive from an attacker's perspective, right? Instead, I could just put in random sequences of words. Now, this is a black box model. It just is input, output. So given any input, it will give you some sort of output, right? So given 17.3 miles Vegas, it seems to think this is positive. And given circle Ford had support, life rulers broken, Jan family, it somehow returns a negative, right? These are meaningless to us. We don't understand why this should be negative and this should be positive. But since I can just rapidly generate random sequences of words, I can issue a lot of queries to this black box, and I can create a data set from this, right? I can create a data set with this random gibberish input and the output of what Google, the Google Sentiment API provides. So I have training data X, and my labels are coming from this black box. So now I can just train, and what we found is crucial here is using a pre-trained model like BERT, and then fine-tuning it on this extracted data from the black box API, even if it doesn't make any sense at all. This somehow ends up working well on real data after you extract the model. So this was kind of a crazy result for us. And we were like, all right, well, maybe sentiment is a very easy task, because you can imagine, even if you're generating random sequences of words, some percentage of the time you might generate some sentiment containing words that do have some sort of correlation to the label. And we know that these BERT-like models are very robust to noise in their data, which is why it's crucial to start with a pre-trained BERT model. So perhaps they ignore most of the random examples, but can learn some sentiment information from the real ones. But it turns out that this same process works well for more complicated tasks like squad, for instance, where this is a QA task where you have to find a span of text that answers the question in a passage. It turns out you can do this as well, as we'll look at later. But of course, this is a huge problem, right? Because if this is possible, then any company that puts out a black box API and thinks they're safe actually is at risk of intellectual property theft. For some types of attacks, you could even imagine getting leakage of the original training data, not the one that I just mentioned, but in vision cases, it's possible. And if an attacker is able to extract a model, then they can also start probing it and find weaknesses in that model and see if those weaknesses, like adversarial examples, generalize to the original victim model as well. So there are many reasons why you don't want people to possess the model that you have created as a company. So here are some of the stats of cost of these attacks that we computed. So we did all these attacks on Google Cloud's natural language processing API, which costs $1 per 1,000 API calls for some number of tasks. And if you wanted to input the same size of the data set as the original Stanford Sentiment Tree Bank, which contains 67,000 sentences, this costs like roughly $62 to do. So you can get 67,000 of these random gibberish input outputs for $62. And if your model can learn from this, then, I mean, that's definitely not that expensive for some sort of attacker. Translation costs more, of course. So how is this different than the distillation stuff we talked about? The most important difference is that here we have no access to the training data as well. So in distillation, remember that we have the teacher model's predictions over the training set that we're training the student model on. Here, we don't have the training data, which is why we have to have some process for giving us these inputs to the API. And that process will hopefully be cheap for us and also hopefully you know, have some sort of useful information to solve the task. Finally, the goal is different. Here, we're trying to steal a model, not compress it or understand it better. Okay, so we tried these 3 tasks: sentiment, textual entailment with the MNLI, and question answering. And we tried 2 different ways of attacking the model. So one is this random gibberish that I already told you about. The other one is not, it's also pretty inexpensive. You just form your inputs by randomly sampling a sentence from Wikipedia. So here, at least, the sentence is grammatically correct English, but it might have nothing to do with the task, right? Most sentences in Wikipedia intentionally are written to not contain sentiment, right? They're supposed to be objective. So it's not like you'll have a lot of positive examples here, but maybe in enough volume, you might have examples. So what do we do when we have something like Squad? So Squad has 2 inputs, a paragraph and a question. So let's take our random generator. First, we randomly generate a paragraph by sampling words. So here you can see this makes no sense at all. It's just a bunch of random words. And then we know something about Squad, which is that usually the question is asking about something mentioned in the passage. So you can construct a question by just randomly sampling words from the paragraph. So here you have an input question, which is a subset of random words from this random paragraph. If I gave you this paragraph and this question, you would have no idea what to do with this, right? But you know, a pre-trained Squad model will give you some span of text within this paragraph that corresponds to this, what it thinks is the answer to this question. So let's take a look at how this does on Squad. The victim model here, the one that Google is using, gets an F1 of 90.6. So this is our baseline. And if we issue about 1 million random gibberish paragraph question queries to this black box victim model and then fine-tune our own like BERT on the result, we get an F1 of 86. So, you know, we have lost some performance, but still, like, this is incredibly high. It's actually higher than what you would get by training something from scratch yourself or training a smaller model and then fine-tuning it on Squad. And you can see that with Wikipedia, if we take 1 million random paragraphs from Wikipedia and make questions in the same way by just like sampling words from that paragraph, we get almost the same performance as the victim model. Without having done anything intelligent at all, we're able to steal this model. And this is quite cheap as well. So one of the key findings from this is that, and this has been supported by numerous experiments since then, is that better pre-training of your model means it's, so your, what do I call it? The stolen model. So this is the model that you're training yourself on the extracted data from the API. If this model is very powerful, like if it's a large pre-trained model, it does better at stealing the victim model than a randomly initialized stolen model or a small stolen model. So as these models are getting better and better and better, it becomes easier to extract things with these stolen models. And yeah, I guess I will, so another thing is, you might be wondering is how does this even work? Like why would these random gibberish sequences, training on them somehow lead to a model that can do question answering on real questions and paragraphs? We did a lot of experiments to try and figure that out, and mostly we're not very successful, but I think one thing that we did learn was that you can kind of measure which of the random queries are most similar to real squad questions, because in this process you will produce some like maybe not reasonable looking to you, but you can still understand why the model might have chosen a particular span of text as the answer given this sequence of words as a question. Maybe there's some like overlap, string overlap or span overlap or something like that. So anyway, the randomly generated examples that look more similar to real squad questions are also much more important for the stolen model's performance than queries that are farther away from the real distribution. So I think it's a combination of these models being very robust to noise and able to learn from the small signal that does exist in this kind of randomly generated setup. All right, any questions?
Why are we going with random generated sentences? Why don't we just choose data that contains sentences for that?
Yeah, so like the best thing you could do is if you knew that there is some publicly available data set ahead of time for the particular task that you're interested in, you could just pass that data set through the black box API and train your model on the results, and that, like the distribution of your input-output pairs would be the same, hopefully, as the actual task itself. But this isn't always possible, right? It's actually quite hard to do for Squad, for example. Like in Squad, to form an input-output pair, you need to have a paragraph and a like a relevant question about that paragraph. So it's difficult to get data like this. Of course, many people have created data sets that are in this format, but imagine a task where there's no public data set available for that task. These kinds of approaches are generically applicable regardless of the task, which makes them of interest to attackers because they require zero effort to scale over multiple tasks.
Did you run any experiments where you kind of tried doing an adversarial attack with a data set that made sense? Like trying to steal them all like that?
You mean like what his question was?
Yeah. Was there an experiment where that actually did?
No, so we didn't try like attacking the model with a data set that made sense because that will definitely work. You have data that is of the form of the task and will teach the model how to perform the task exactly like you would use that model after training it. So that would just basically be like kind of domain transfer or something like that, which there have been many works on. This is more like, it's not even English, right? It's some random thing, but it's still kind of surprising that it allows you to attack these models in this.
I guess I would think that feeding it random stuff might even tell you more about the model than feeding it something that makes sense. Like, if you feed it something that makes sense, then it's going to give you some sensible output. Versus if you feed it something random, you don't know what it's going to give you. So when it responds to you with something, now you can, because there's high uncertainty before, you can now update yourself based on that. So I think we're stealing the model.
So what you said makes sense, but at the same time, you are only receiving examples that are out of distribution for the model, right? But then when you actually want to use this model, none of the examples that you put in will look like any of those examples. So you might be learning about all of these different like edge points of what the model will do in this case, in this case, in this case, but you're not ever learning about what the actual in distribution samples, what the behavior should look like. Or maybe like you obviously are because it works in that case, but it's not clear how exactly. And our theory is that some of the points that we think are out of distribution are closer to those, the actual real natural language examples than initially we would think, and they require the same types of reasoning to solve, and but it's very hard to measure, of course. Sorry, what did you say? Yeah, so let's say I'm doing sentiment analysis. So here I'm just generating all these random sequences and getting the associated label. Sometimes I might generate something like 17.3 miles, awesome, Vegas, right? The word awesome is, like, if I gave this to a human, they would probably say this has positive sentiment as well, just because of the existence of that word awesome, right? So we might call this random query as closer to the real natural language distribution of sentiment queries than like this one, which has no sort of sentiment and is also not English. So some of the queries that are generated are more useful, and they're actually contain some sort of sentiment words or something like that, and those seem to be more important than other random queries. Okay, so a sad finding also is that there's no real defense against this kind of attack. As long as you have an API that has inputs and outputs, someone is going to be able to extract that model with at least some fidelity to the original model. We explored a couple of defenses, and since I think there's been more work on watermarking, but it's a very limited defense, so we'll talk about both of them here. So in watermarking, the idea is that you as the company who's serving the victim model you are aware that there could be these potential attackers who want to steal your model. So what you're going to do is, for some very small fraction of queries from a single user, you're going to intentionally produce the wrong output. So maybe like 0.1% of queries, you produce a wrong output and you send it to the user. So you're here assuming that the user will tolerate some percentage of the queries being wrong, or at least some percentage being more wrong than they normally would. Every time you decide to intentionally return the wrong answer, you store it in a database. This is called a watermark. So then, let's assume that someone steals your model, and let's say it's a rival company. So let's say Google has a sentiment API, and then Microsoft wants to make a sentiment API. So instead of making their own, they just steal Google's and then host it as their own API on like whatever their service is called, Azure or whatever. So here, now let's say Google wants to know whether Microsoft has stolen their model or not. This is the only setting in which watermarking is effective, is when the attacker makes the stolen model publicly accessible through an API. Then Google can run all of their watermarked queries through Microsoft's API and see whether or not for each of those instances the Microsoft API is returning the wrong prediction. Because if it is, that's a strong signal that they have stolen this model that Google is serving. You can imagine that this is not a great defense for many reasons. What if the attacker decides to use the model privately and not put it on like a public API? In that case, you would never know because you don't actually have access to their model. You have a question?
Is there any legal precedent around watermarking? Has it been shown to be sufficient evidence to show that?
That's a great question. I don't think so. I actually don't think anyone has successfully used watermarking, at least in public knowledge, to even make a claim that someone has stolen their model. So this is all like theoretical. It could be a potential defense, but as with many things in security, they study scenarios that could be completely impractical but are still kind of interesting. I don't actually know, since we worked on this, if there have been any success stories with watermarking, but again, the situation in which it's useful is probably quite rare compared to the majority of cases. Okay, so that's watermarking, and there are some simple ways to defend against watermarking. The general idea, though, is that the stolen model will memorize the watermark data. So it will memorize the wrong label for these particular examples, and that's a good sign that you know, it hasn't been trained legitimately, it's just been stolen. Okay, so I'm gonna skip over all of this and go to these limitations we've just discussed. One, watermarking, the effectiveness depends on the the stolen model being publicly accessible. And limitation 2 is also very important. So there's a very simple way to get around watermarking, which is to do double extraction. So you extract the model once and then extract it again on top of the extracted model. The idea is that the second model probably does not memorize these watermarks in the same way. So this is like the simplest possible defense and kind of renders this. I think there are now papers that are focusing on this double extraction setup, but as you can see, this is just like an incredibly specific situation where, yeah, you assume the attacker might be doing double extraction, so what do you do then? Okay, so another form of defense is membership classification. So this one is a bit more useful, but it also has the same limitations. So here, you're basically going to run a classifier to determine whether or not a particular input query is legitimate. So you could imagine if an attacker is using random sequences, you could just simply deem all of their queries as illegitimate because no one would ever want to know the sentiment of some random gibberish. And so if your classifier detects that this particular input is out of distribution, then you can return a random label instead of returning the model's predicted label. However, it's unclear, like, if the attacker is slightly more intelligent, then this becomes kind of iffy, because let's say the attacker is using random Wikipedia sentences. Now this is much closer to a real legitimate user's queries. Even if they're slightly off, it could be really bad for you to start returning random labels for these kinds of queries, because a legitimate user might also issue them. So that's the kind of issue with this, is that if the attacker is slightly more intelligent than using random queries, it probably doesn't work. That said, you can train pretty good membership classifiers on both random and Wikipedia strategies using like a classifier trained over the final layer representations. But again, this is quite limited. No company would implement something like this because the risk to real users is just too high. Yeah. Okay, so yeah, that was a quick overview of distillation's uses both to compress and also kind of to attack, although there's a difference between model extraction and distillation in that we don't have access to the training data, and we also don't have access to the full distribution of the model, but it's still kind of similar. Okay, any final questions anyone had? Yeah.
The like victim model and the thief model, do they, in the experiments, do they have the same architecture?
Oh, yeah, that's a good question. I didn't mention it. So we tried both settings. One where we knew the identity of the victim model, like it was, you know, Bert with this number of layers or whatever. But that's not a very reasonable setting, right? Because the company probably isn't going to publicize what their model is. So we also tried mismatched architectures where the victim model was different than the stolen model, and it actually seems to work just as well. And in fact, you can do better if the stolen model has a bigger, more powerful architecture than the victim model. So it does not seem to rely on the matching of the architecture. Also, I should mention that since this work was published, there was another effort by a group from UC Berkeley that extracted Google Translate. And they did this all, there were some legal issues with the publication of this paper, but you know, Google gives you, if you are using Google Cloud, a credit of $300 and for every account. So this group used like a bunch of these accounts to get issue a lot of queries to Google Translate. And then it was quite straightforward to actually train their own translation system on the extracted data, and they got like the blue scores of their extracted model were very close to Google Translate on a number of language pairs. So yeah, I mean, like Google Translate is a hugely valuable piece of software. So this is definitely a concern. I think, again, there are no good defenses against this. So yeah, definitely something to keep in mind if you go off and work at a company that's serving these models. Is you might want to monitor at least the usage of some of your your users. You mean why don't companies just steal each other's models? Well, the stealing process does result in a worse model in most cases. So most companies are their main focus is on performance. So even like a 0.5% improvement in accuracy is a big deal for a company. So if you're going to steal a model and you get like 95% of its predictive ability, that's probably not good enough, right? Yeah. Yeah. Yeah, I mean, it depends on the use case. Like if some performance drop can be tolerated, then maybe it's a viable solution, but I suspect usually that's not the case. Yeah. All right, so see you all next week, and hopefully you're progressing well on your projects.